So now we can start our tutorial. So last week we already done some quizzing for quiz 1. So we will continue to Q7 in quiz 1. So the problem is which edge in this network is a bridge, and which edges in this network are local bridges but not bridges. So let's see. I'll give you 2 minutes for you to think about it. So let's look at the question together. Firstly, let's review the definition of bridge and also local bridge. Edge is bridge if we remove it. Say the AB here, if we remove it, the whole graph will be disconnected. And the local bridge is like the edge. If we remove it, and the whole graph is still connected, and also they have no friend in common. So in this network, so we can try, firstly, which edge is a bridge. So we can try to delete each edge to see if after we remove it, if the graph is still connected. Say we remove AI here, the graph is still connected, or AE. We just keep trying this. You can see, I think it's easier, right? If we delete IJ, the graph will be disconnected. All the other edges, if you remove it, the graph is still connected. So we say IJ is a bridge. So what about the which edges in this network are local bridges but not bridges? So according to the definition, we can find for each edge we can like check if they satisfy the definition. Like for edge AI, and they need to have no common friend, right? Right. So no common neighbor, but they have E as common neighbor. So AI is not a local bridge. And we just keep trying. For AB, the same. It's not local bridge. B, same. And IJ is a bridge. And also after we remove it, the whole graph disconnects, so it's not a local bridge, it is a bridge. Similar for other edges. But when it comes to edge, HK, you can see HK, they have no common friends, right? No common neighbor. And if we remove it, the whole graph is still connected. So we can say HK is a local bridge, but it's not a bridge. The answer is like IJ is a bridge, HK is a local bridge. So to find a local bridge, you can also use like counting the triangles, listing the triangles in the network, because if edge is involved in a triangle, that means it is definitely not a local bridge, right? So for example, this triangle AIE, that means these three edges, they are not local bridge. And this triangle, that means these three edges are not local bridge. Similarly, we just keep listing all the triangles, and then we only have these two edges left. Then we can check. Is there any question about this problem? Okay. If not, let's move on. Next question is, in the figure below, which nodes violate the strong triangle closure property? So we can review the strong triangle closure first and trying to see what's the answer here. I'll give you 2 minutes also for this question. Okay, so let's first review about the strong triangle closure. So the strong triangle closure is like two strong ties will imply a third edge. Like here, A has two strong ties, A to B, B to C. Then there will be an edge between B, C. So to solve this problem, we just check for each node if they satisfy the property. So for node A, it has these two strong tie, and there is an edge between B and D. And that's it for A. So A satisfies the strong triangle closure. Now for B, it also like it has these two strong tie, AB and BC, and there's edge AC here, so it's okay. But for BC and BE, they are both strong tie, so there should be an edge CE here. Then it can satisfy the property, but it doesn't have, so node B violates this strong triangle closure property. And for node, we keep checking. For node C, has two strong tie, CBCD, there is edge BD, so it satisfies. That's all for C. And for D, D has DA, DC, AC is here, and DC, DE, there's a missing edge here. So D also violates the property here. And next we check E. So E has two strong ties, and B and ED, and BD is here. So E satisfies. So the answer is B and D. Is your answer same as this? Any questions?
I'm sorry, can I ask one question?
Yes, please.
Yeah, I mean, for example, like if there is a strong tie between A and D and another strong tie between C and D, so I mean, for the paths between A and C can either be strong tie and either be weak tie. Am I correct?
Yeah, as long as there's the edge, there's a connection between them.
Okay, thank you.
So there's the answer. There's a question. Okay, I will repeat it. Only one of them is fine. Okay. So for example, for node B, so let's check if B satisfies the strong triangle closure here, right? So for B, B has two strong ties here, BA and BC. So according to the strong triangle closure, there must be an edge between AC, because AC are both strong tie connected to B. This is it clear? This step, can you understand? Yeah, okay. So next, we also check the other strong ties for B. Like for example, BC and I just try to make it clear. So for BC and BE, if you understand this, BC and B, they are strong tie. They, according to strong triangle closure, then there should be an edge. So that's why we say B violates this strong triangle closure. Yeah, okay. If you got it, it's fine. Okay. Any other questions? Okay. Now let's look at the question 9. So look at this network. So please calculate the neighborhood overlap of edge BC. To help you, I already gave the related contents here. So I'll give you 3 minutes for you. Okay, I see some of you already shared your answer. Thanks for sharing your answer. So let's work it out together. So the neighborhood of edge BC, the neighborhood is defined like this. Let's say, so firstly, we need to find out the neighborhood set of these two endpoints, B and C. So for NB, includes the neighbor of B, which we have A, D, and E. Remember, we don't include C in the neighborhood of B. This is the definition. So for neighborhood set of C includes A and C to D. So we have A and D here. So the intersection of these two sets would be A and D, right? And the union of these two sets will be ADE. So the answer is 2/3. That's the answer. Is it clear? Any questions? Okay, good.
Could you go over question 8 one more time, please?
Question
8.
8.
Yeah.
Yeah, what's the question?
Could you just explain your working out again?
Any volunteer who likes to, because I already explained twice. Any volunteer who likes to explain? What's the point like you don't understand? Like the answer is B and D. Is there any part like you don't understand? Like why, for example, why B violates the strong triangle closure?
Yeah,
no?
like I tried to like understand it, but like I can't wrap my head around it.
So see, the triangle closure is like this, right? If a node, it has two strong ties, then there must be an edge between these two nodes. Is this clear for you? This is strong triangle closure.
Yeah.
Yeah, okay. So for B, we can see B has two strong ties like BC and BE. There should be an edge here, CE, but in this graph, it doesn't have this edge. That's why we say B violates the strong triangle closure. It doesn't satisfy this property.
Right. Okay. And then for D, it would be between A and E, but there's no edge
Yeah,
between A and E. Yeah.
AE
Okay.
or CE.
Yeah.
Like it's just not just one. Yeah.
Oh, okay.
Okay.
Thank you.
No problem. Yeah. Thanks for the thanks Ziqi. If no more questions, that's the quiz 1. Now we can go to quiz 2. Let's see. So the first question. So let's say we have going random walk, and the links will be formed to the existing nodes at random, and with this value, like that is for the new node, there will be 5 new links. formed by this new node and with the existing nodes. So in this setting, what is the expected degree for the node 8? That is the 8th ball node. At time t equals 10, that is like when the 10th node is added in this random walk, what's the expected degree for node 8? I'll give you 3 minutes for this question. Okay, let's work it out together. So we have this growing random walk. So let's assume we already have this 7 nodes added. They are connected to each other. It doesn't matter how they are connected for this problem. So let's say we are adding a 8th number, which is the node number 8. So it will have 5 edges connected to existing these 7 vertices. So whatever whoever they connected to, node 8 will have degree of 5, right? Degree of 5. And now we add a node number 9. And now for this node 9, there will be 5 edges, and each edge will be connected to this 8th eight existing vertices. So the chance of selecting 8 is 1 of 8, but there will be 5 edges. So the expected degree of adding vertex 9 is 5 of 8. And we continue to add node number 10. Then the new edges between node 10 will be edged among these 9 vertices. So the chance of choosing 8 will be 1 over 8, but there are 5 edges, so the expected degree of 8 is 509. So the answer will be 5 plus 508 and 509 is D. Any questions?
Sorry, I have one question. As regarding the answer of D, why we do not use 5 is divided by 10 instead of 5 is divided by 9? It's because the 10th node is just born, so it cannot connect with the existing nodes, right? So that's why we use 5 is divided by 9.
You mean this?
Can I understand this? Yeah.
Because like 8 and 10 is already like one end of these new edges. These new edges actually are connected with 10 to other 9 nodes. So we are choosing from these 9 existing nodes as the other endpoint of these new edges.
So we only choose the existing one, right? We only choose the existing, not the total.
Yeah.
Okay.
Because like for 8, there are 2 endpoints. One is definitely 10. We are just choosing among the other, the other 9 existing nodes.
Okay, good. Thank you.
Any other questions? Okay. If not, let's go to the next question. So, the following is a scale-free network generated by from BA algorithm. Let's say we use m equals 1. So this is like for a new node vertex, you will have 1 edge connected to it. So now we add a new vertex to this network. So what's the probability that this new edge of this new vertex is connected to node 6? And what is the probability that the new vertex has edge with node 3? I'll also give you 3 minutes for this question. Thanks for sharing your answer. We can work it together. So first, let's review the BA model. So remember here, when adding a new node, the probability like this node is connects to other nodes is proportional to their degree. So here in this network, so the probability that this new vertex it is connected to any vertex is proportional to their degree. So we can like count the degree first. Like for node 1, degree is 3, node 2, degree is 2, 3 degree is 1, 2, 3, 4, 5, 4 is 3, 5 is 2, 6 is 1. So the chance of selecting vertex 1 is 3 over, so the total of these degrees, sum them together. So 3 plus 2 plus 5 plus 3 plus 1 plus 2, that's 16. So the chance of selecting node 1 is 3. Oh, so we're asking node 6. So the probability will chosen 6 will be 1 over 16. And for vertex 3, that will be 5 over 16. That's a probability. Oh, there's 2 nodes. Is there any question? Yeah, like Yuan shared answer, you can also put like what we introduced in the lecture, put all the endpoints of all the edge and random choose or count the occurrences of them. It also works. Okay, if no question, let's move on to next one. So the following 2 questions is just the aim is just for you to understand the concept of random walk and scale-free networks. It's not like a formal definition. So just one thing I want to remark. So question 3 is like this. So for the paper citation network, where a node represents a paper and an edge, that means a paper is cited by other papers. So for the paper citation network, is this like a random walk? Yes or no? Just half a minute, you can figure it out. Yeah, the answer is no. It is not. Paper citation network like we introduced. Usually, some paper, a few of the papers, they have really high citations. And many papers, the citation number is very small. So it is more like a scale-free network. Yes, it is. It's not a random network. So question 4. What about this network? It looks like a scale-free network. Is it yes or no? Yes, yes, it is. Because in a scale network, the degree distribution is satisfies Power law. So a small number of the vertex has really high degree, and many nodes will have really low degree. So in this network, we can see like many of these vertex, the degree is very low. But like a few of nodes, like they have really high degree. So this is more like a scale-free network. So like I mentioned once again, it's not a formal definition, just help you to understand these concepts. Any questions about these two problems? Okay. If no questions, let's go to the fifth question. So in the basic 6 degrees of separation, one asks whether most pairs of people in the world are connected by a path of at most 6 degrees in the social network, where an edge joins any 2 people who know each other on a first-name basis. That's the 6th degree of separation. So now let's consider this. Suppose that we consider the full population of the world, and suppose that each person in the world, we create a directed edge only to their 10 closest friends, but not to anyone else they know on a first name basis. So if we do it like this, in the resulting closest friend version of the social network, is it possible that for each pair of the people in the world, there is a path that at most 6 edges connecting this pair of people? In this setting, do you think, is it possible? In this way, is it yes or no? Yeah, so someone already posted his answer. No. Yeah, so actually in the lecture we already like a similar situation is like this. So if we only connect to like one person, only to 10 closest friends. So with one step we will reach 10%. In second step we will reach like 200%. And this in 6 steps we will only reach like this much of person. And this is like we have like 7.8 billion people in the world. This is like far less than this number. And also because of the triangular closure, so the actual number of people we can reach is actually also smaller than this number. So the answer is no. It is not possible. Like any 2 people will be connected by at the most 6 degrees, 6 edges. Is that any questions?
Sorry, just one question. Like for this question, like it said we create a directed edge only to their 10 close friends. So can I understand this situation like we have high clustering coefficient? but not to anyone else they know on a first name basis. So which means we have low average shortest path. It's not like this reason.
Sorry, can you repeat your question?
Yeah, I mean for this question, like because we like the question suggests we create a directed edge only to their 10 close friends. So can I understand this situation like we have the high clustering coefficient, but not to anyone else they know on a first name basis. So is this situation like we have a low average shortest path?
This is just for you to understand like this situation, like we have this triangular closure. The point is not about the creating a graph like with high clustering coefficient, or like the situation, the limitation here is like we just tell you like the number is 10 is small because we only connect to closest friends, not like only like any people we know, any acquaintances. Yeah, that's the point here. Yeah.
Thank you.
Yeah. If no question, that's all practice for today. Yeah. So if you want to use this chance to talk to your teammates or like no other people, or like maybe find your team, you can stay and talk to each other, or use the chat box to chat with other people. Yeah, for the tutorial, that's it.
Sorry, Shibo, can I ask one question about our lecture?
Mm-hmm.
Yeah, at the end of the lecture, you mentioned like during the week 5, each of the group leaders, the leader should submit an email with our proposed the topic. So like what is the proposed topic? Is it like the name or the proposal of our topic?
Yeah, you can give us some information about your like about your project. If you choose any from this provided topic, you can just give the name. But if you chose your own topic, you can give some more information. Like, some people choose from these different categories, and like what's the topic of your project, and like what problem you are trying to solve. That's the main thing. And what if you can also give us some information about your data set, is also helpful. Yeah.
So if I choose the topic like the movie recommendation, it's from the project topics. Yeah. So do we need to write a proposal like what kind of algorithm we're gonna apply in the assignment, something like that, like the summary, something? I don't know.
No need. You just tell us it's topic 2, movie recommendation.
Okay. Thank you.
No problem.
Oh, good.
No, that's all. We're not yeah, the tutorial is already to the end, so nothing else. Just yeah, if you want to stay, you can talk to other people, or if you want to leave, you're okay to go.